Good afternoon, everyone. My name is John Gravel, and I lead the Gas Analytics and Detection Group here at Lesman Instrument Company. And I'd like to thank you for joining us for today's session, which is going to focus on the fundamentals of thermal conductivity analyzers and applications where they can add significant value. During today's session, we're going to focus on fundamentals of thermal conductivity detectors, recent advancements in miniaturization and the cost reduction that can be achieved from these advancements, improvements in the calibration process, a review of common applications where thermal conductivity analyzers can add value, a discussion on sample systems, and we'll have a time for questions and answers at the end of the presentation. Our speaker for this session is Narj Svarajas of Panametrics. Narj is the global technical sales leader for process analyzers based out of Boston. He's been with Panametrics since 1990, working as an application engineer, key account manager, marketing and services leader, and product manager. He's a legitimate expert in gas analytics. We welcome Narj and his experience and knowledge and appreciate him sharing his time with us. Please note that during the presentation, microphones are on mute, so use the question section and chat box for any questions or comments. We'll make sure that we weave them into the presentation or address them at the end in the Q&A time. With that, I'm going to turn it over to our speaker. Narj, the floor is yours.
Thank you, John. Thanks, folks, for joining today. Today, as John pointed out, we will be covering the fundamentals of thermal conductivity for measuring one gas species in another, typically in the % range. We'll talk about what advancements we've been making for installation simplification and cost reduction through miniaturization, ease of use and reduced time for calibration. And then we'll spend the bulk of the time on applications where a binary gas analyzer can add value. The sample system designs I've chosen to build in during the application session, so you can see in many of these cases where the sample system design comes into play. And then at the end, we'll obviously have time for tools, for questions and answers, etc. So let's get this kicked off by talking about what is thermal conductivity. Keeping it very simple, thermal conductivity is the amount of heat that will flow through a material in a certain amount of time over a specific distance per degree of temperature gradient. Really simplified, what it means is if you have a hot spot and a cold spot, heat will travel from one to the other, and the ease with which, or the rate with which the heat will be transferred and the speed at which it happens is what we're talking about here. How many calories per centimeter per second per degree C difference. Different substances, gases, solids, liquids, all have thermal conductivities. Today, we're going to talk predominantly about gases, okay? To keep life a little simple, what we have is a term called relative thermal conductivity. And relative thermal conductivity is the thermal conductivity of any gas as it relates to air. So that air, or nitrogen, if you will, is divided by the thermal conductivity of nitrogen is equal to 1 by definition. And what you can see here is a graph that shows you the different relative thermal conductivities of these different gases, with 1 being air and everything else on that scale. So if you take a look on the far right hand side, you see that hydrogen is around 6.8, 6.9, and a very big difference in thermal conductivity compared to that of air. So a lot of the applications we're going to talk about today involve hydrogen, but that's not necessarily exclusive. So for instance, we might be talking about carbon dioxide and methane. And even though the difference between air and hydrogen is much larger than the difference between CO2 and methane, it's still a great application for us with plenty of resolution. The table to the right shows you the relative thermal conductivities from many different species to show you the variety of gases that you could use a thermal conductivity analyzer for. Okay. How does it work? Physically, how does it work? You require 2 thermistors, one that's sealed in a reference gas, in this case air, and then one that has a sample going through it. These thermistors are kept at 150 degrees C. while the transmitter itself is kept at 55 degrees C. And what happens is that these thermistors are obviously, because of that temperature difference, are giving off heat. And that heat has to travel through the sample gas on the left and the reference gas on the right, in this case, air. Now, if you had air going through both of these, the rate of change would be the same. The amount of heat going from the thermistor to the wall of the analyzer would be identical in both cases. But if you have a different gas going by there, whether it's your zero gas, your span gas, or something in the middle, the heat given off by that thermistor is going to be different in terms of the amount of the rate at which it's transferring that heat from that hot thermistor to the walls of the sensor. What you see at the bottom is a schematic of a very simplified Wheatstone bridge that shows you that the thermistors are in a Wheatstone bridge, and the amount of voltage it takes to get that back in other words, the amount of microvolts that is required to keep these both thermistors at the same temperature is a measure of how different those two relative thermal conductivities are. And that relationship is in fact linear. So this makes a very simple circuit to calibrate, putting your zero gas by, putting your span gas by, and then improved display package that accepted that 4 to 20, powered the transmitter, and then was able to send whatever signal you needed back to your PLC or your DCS. Again, a 4 to 20. And that was programmable. You could get to most of your parameters right from that display package. But that required two pieces, a blind transmitter and an external display. So this year we decided to pull the whole thing together into one unit and build the display right into the XMTC, and the new product is called an XMTCpro. So now where you had two pieces required to make a complete measurement, now you have a complete analyzer that has an integral transmitter to it. This gives you a feel for how this comes together. So if you were to take and open the top case here, you can pull the electronics and the measurement cell out as a complete assembly. And this shows you if you were to take the display off and where that comes into play here also. So all of these interconnect inside the explosion-proof enclosure here. The flame arresters are installed for certified installations in hazardous area. So here at the bottom, you see there's nothing attached. You would have flame arresters here if it was going into an explosion-proof area. There are 4 entries, one for power, one for your relays and alarm contacts, one for your digital output or communication, and one for your 4 to 20s coming out. So what advancements did we make? What were the advantages of going to a complete transmitter with display as shown in this sample system over here? It is SIL 2 by design, and what you'll see in our application section that there are several applications that require SIL, or that at least that the customer is preferring SIL today. In fact, we can go to SIL 3 with redundant transmitters as long as you have separate power supplies to these. Additionally, we've added Modbus communication, and you can see a Modbus map at the right-hand side here. So you can communicate via Modbus, change parameters, take your readings via Modbus, etc. Complete Modbus map for everything that you can get on the display, anything you can program in the transmitter, you can get on the Modbus map. You still have 2 analog 4 to 20 outputs, one for calibration data and one for calibration data range, and one if you wanted let's say a tighter range or a larger range. So you can get 2 4 to 20s out of the transmitter. And then you have 4 alarm contacts and 11 different factory calibration ranges that are available to you, and 2 different cell temperatures. So by having 11 standard calibrations, it makes it very simple for our application engineer to find the most relevant range and calibration scheme for you, And if necessary, we can get you a special calibration range. 2 different cell temperatures allow you to be operating at 55 degrees C, but in some very hot regions and or very hot applications, we actually have a high temperature range that allows you to operate that sensor at a higher temperature to take advantage of maybe having some liquids that might condense at a lower temperature, or in some very high temperature cabinets where you cannot get sufficient cooling. Again, application engineering team will help in that respect in terms of choosing the correct temperature for that cell to get the maximum performance out of that transmitter. Cost reduction through miniaturization. And by miniaturization, we basically eliminated the need for an external display. And the second piece of this is that you now have you can actually get away with a lot less headroom between the top of this transmitter and the box. In the past, with the XMTC, you actually had to take the top cap off and be able to look into the transmitter in order to do the calibration. It was a push button and a couple of lights. Very simple procedure to do the calibration, but you still needed access into the top. Now all of your calibration is done from the front keypad, requiring less space requirement on the top of the transmitter. And without a second display, and without the conduits having to connect it to, it really does help in terms of the footprint on the plate. And space is money. So all of this, smaller cabinet for the sample system, less headroom for the requirement for the transmitter, all comes together to give you a lot less real estate on the plate, smaller box, lower cost. Ease of use and reduced time for calibration. With a simplified display built right in here with a graphical user interface, not so many words, lots of pictures, really makes it simpler to be able to get to the calibration section, makes it simpler to be able to enable the calibration and to complete the calibration. You probably don't need a manual, but maybe the first time you will, just to get started and get a feel for the where everything needs to be. But after that, when you approach a transmitter and you have your cal gases set up, it would be just takes a few minutes to do the calibration. Time is money, and this makes it a lot easier so you don't have to spend a lot of time trying to figure out how to calibrate this transmitter.
Hey, Narj,
Yes.
sorry to interrupt, but we got a couple questions.
Wow. Okay.
How frequently do you need to calibrate? How often do you calibrate?
Our recommendation is when you first get the transmitter, calibrate it out of the box, make sure, or at least put the cal gases on the transmitter out of the box, and make sure that everything is working properly. More often than not, assuming that you haven't had this sitting in a box somewhere for months and months and months, you probably have to make no adjustments right out of the box. My recommendation after that is do your first cal, or at least a verification 3 months down the road. And then again 3 months after that. That'll give you an indication as to how stable that calibration is in your application. After that, that'll give you a sense of whether it should be every 3 months, 6 months, or yearly. A lot of it has to do also with how accurate you need the transmitter to be. If accuracy is not critical, if this is more for trending, then you can get away with once a year, or maybe once every 6 or 9 months. If absolute accuracy is critical, as if this is in a safety type application, and if you are running close to the alarm point, that will dictate a more frequent calibration.
Got it, thanks.
Yeah.
The follow-up question, second question, which is similar. How long do these things last? I guess that's a question about the detector.
Yeah, that's a great question. The XMTCpro replaces the XMTC in our product line, which replaced the TMO2TC before it. The TMO2TC was an analog transmitter where you actually had to use potentiometers to bring the 4 milliamp in and the 20 milliamp in. We are still getting phone calls for service on those transmitters. And those have been working now for 25 to 30 years. There are no moving parts. There's nothing to be consumed. There are no spare parts. There's nothing that actually changes with time. Could something burn out? Of course. Can a microprocessor chip fail? Yes. But other than that kind of a failure, these will work at minimum several decades without any need for any kind of maintenance to them.
Perfect. Thank you.
Quite welcome. Finishing up on the slide, the Modbus enabled remote calibration is a feature, especially that's really useful if you want to be able to set up solenoid valves and do an auto calibration. Being able to enable, let's say, the system to go into a cal mode and then flow a zero gas and a span gas without you having to physically be there. Now that takes a little bit more work on the DCS side or the PLC side and the control system, but if it's located in a difficult place to access, that makes it a lot simpler. All in all, the entire look and feel of how you do calibrations today is very much simplified. Now we enter all the fun on the fun part. Where do you use these, or where can we use these? And for the folks on the phone, feel free to ask about your specific applications once they come up on the screen, or if we don't touch one and you have an application space, we can obviously talk about that also. Let's jump into the power industry and some of those applications. One of the most prevalent applications for a binary gas analyzer, especially one that uses thermal conductivity, is hydrogen-cooled generators. Because of the spinning components inside of a generator, they generate a lot of heat. And it's important to move that heat away from the blades, okay? And hydrogen has a very high thermal conductivity. If you remember correctly, it was out all the way to the far right-hand side where air was at 1, 7 for hydrogen and roughly 1 for air. But you can't just keep running these without maintenance. And the nice thing about these is that the idea is that you want to make sure you're not getting air, or more to the point, oxygen that comes in through air in there to cause an explosive limit. So there are really 3 applications here: air and hydrogen. You want to keep that air from knowing that the air is not getting in there to cause an explosion. But then when you do need to take the generator down, you need to backfill it with carbon dioxide first to remove all the hydrogen before you bring air in so that people can work on the unit. So you have 3 distinct applications: air and hydrogen, CO2 and hydrogen, air and CO2. After you're ready to get started again, you do need to replace the air that's in this hydrogen-cooled generator with carbon dioxide, push all that air out, and then you need to backfill with hydrogen, pushing out the CO2. So you actually have 3 applications for this transmitter. And here's what they look like. What we would do is we would call 4 milliamps carbon dioxide, and your span gas then is hydrogen at 20 milliamps. And air would fall at or around 5.5 milliamps, okay? The transmitter then would hold 3 calibration curves. You would hold curve 1, which would be your air and hydrogen, which is 5.5 to 20 milliamps. Curve 2 is your full range scale, and curve 3 is in fact your 4 milliamps to 5.5 milliamps. So by having 1 transmitter, you can actually do 3 applications, or 3 portions of that 1 application.
Narj, I'm sorry, a couple more questions. Do you need to flow the gas?
Yes.
I think what they mean is, do you need a flowing? I think I'm reading here, and whoever asked this question, please clarify. Do you need a flowing reference?
Do I need a flowing reference? No, I do not need a flowing reference. In fact, remember in the second slide that we actually had one of those thermistors sitting in a sealed reference, and that sealed reference is dry air. And that gives you your reference point. So there's no need for a flowing reference. But you do require a constant flow of your sample gas. It will not work in a stagnant situation. So you can't use this, let's say, as an area monitor, because you won't get diffusion up into the measurement cell. You do need to pull a sample through the transmitter. So I'm hoping that I've answered the question 2 different ways.
And there's another follow-up question. Do you use Modbus to tell? So if, do you have to switch the curves? How do you switch the curve?
You can do that either through the front panel or through Modbus.
Okay.
Yes.
Thanks.
Yeah, so you could choose curve 1, curve 2, and curve 3 right from the front panel. That is less convenient, obviously, than doing it through Modbus. And here's a situation where, in this application, we can talk about sample systems directly. So if you take a look at the panel on the left-hand side, this was used for these applications for many years by one of our customers who is who has hydrogen cooled generators on their, and they put these on each one of those. And yes, you'll see 2 displays here because they have 2 transmitters. Both of them are actually on the back side of this plate. And you can tell by these lifting lugs here, that these are exceedingly heavy panels. They were made to be pretty much bulletproof. Since then, we've moved to a much lighter and much simpler design, and that's shown on the right-hand side with the XMTCs and the display packages. Now, given that we're going to an integral display on our transmitter, you would now have the display right on the transmitter itself. You would not need the displays in the upper left-hand side on that plate. And in theory, you can make this plate almost half the size that it was originally designed for. Okay. And yes, these are done. That you are always going to have a redundant measurement here, folks. Even though they, regardless if it's SIL2 or not, they're going to have 2 transmitters per plate for redundancy purposes. It is that important in measurement. One other application in the power industry is actually a nuclear power application. In the event of a reactor coolant failure, hydrogen may form as steam reacts with a fuel rod cladding. The hydrogen is removed by catalytic recombiners, converting oxygen and hydrogen to water vapor. You don't want that buildup of hydrogen there. And the XMTCpro would be monitoring the hydrogen typically to less than 0.5% by volume, even though the LEL, the lower explosive limit would be closer to 4%. They typically don't want to get anywhere near there. So they're always looking to see that they're below 0.5%. If we move away from hydrogen for a second and go to biogas and landfill gases, in biogas that comes from landfills or as a product of anaerobic digestion. And then typically those gases are saturated with water. This gas is typically used as a fuel gas and then upgraded to biomethane. Typically in these applications, oxygen is also measured, and because it wants to be under 2%. So let's just take a look at this. So what you typically have in these applications is the raw gas, whether it's a biogas or a landfill gas, is going to have methane and it's going to have carbon dioxide. If it's rich enough in methane, and if there's a local use for it, the customer may choose to do nothing. They just may use it as a fuel gas, burn it, and go from there. Especially if whatever they're burning with or for, the generator, for instance, can take a high CO2 content gas and burn it. Okay. But typically what you'll do is use some kind of a membrane separator to separate the CO2 from the methane. in which case you may want to know the hydrogen, the methane CO2 blend going in, the CO2 purity on one side of the membrane, and the methane purity on the other side of the membrane. Because don't forget, you're going to be taking these gases and then doing something with them. The CO2 may be cleaned up and sold. It may be sequestered. The methane will be cleaned up and then either used locally or pumped or brought up to pressure and put into the grid, into the natural gas grid. The other measurement that's typically made in this case is oxygen. Oxygen is measurements used to make sure that as you're pulling gas out of these landfills, that you're not sucking in air into the landfill. Because if you get air into the landfill, now what you'll end up is with an explosive mixture of oxygen and methane, and something like a spark or a lightning bolt would actually blow up your landfill. And that makes a big mess. People want to avoid that at all cost. Okay. And on the right-hand side, lower right-hand side, you see a typical sample system for this. And the sample system here is designed to do two things. One, be able to provide sample versus cal gases, and then a zero versus a span. But the more important part of this sample system is to be able to drop out any liquid water that might be condensing. Because don't forget, these gases are saturated with water because they're underground or as part of an anaerobic or aerobic digester. And in that case, you want to be able to drop out the liquid water before it gets to the transmitter. In many cases, the gas is dried before it's even sent there. It might be chilled and or dried to knock out the water vapor so that you do end up with only a binary gas mixture. In other words, CO2 and methane being the only two things that are moving and the water vapor not being part of that equation.
Narv, sorry, I got a associated question. What about corrosive gases? I think they're asking about hydrogen sulfide.
Yeah, the hydrogen sulfide is not a problem. Everything is going to be of the right materials, typically stainless steel, but we can even go to materials such as Hastelloy. The thermistors that are in there are glass sealed, so typically, again, not an issue with corrosive gases like hydrogen sulfide. Even carbon dioxide can be a corrosive gas in that you can get carbonic acid if you have enough moisture and oxygen. So no, these are very simple applications for the transmitter. The small amounts of H2S that might be there are not a problem. In fact, if we were to look closely at this panel that has 3 thermal conductivity analyzers and an oxygen analyzer, you'll also see an H2S transmitter here, just to feed back the H2S measurement to the PLC. So in essence, no, there is no issue with the hydrogen sulfide or with corrosive gases. And in theory, we could use this to measure one gas in something like chlorine, for instance, or as long as it's 1% levels of one gas in another. Again, it's just a matter of choosing the right materials of construction and keeping things relatively dry.
Got it. Thanks.
Welcome. In a CCR unit, there's hydrogen being fed in. There is your feedstock coming in, and then you have your product coming out. But in order for the reaction to go to completion, you do not typically use stoichiometric amounts of hydrogen. You don't try to do the chemical reaction one for one. You will always put in more hydrogen that's needed to ensure that you have the reaction go all the way. And then what you'll do is monitor the recycled gas for things like moisture. But the more important piece here is also for the health of the reactor is to take a look at the hydrogen quality or the amount of hydrogen that's coming through, or more to the point, how much of it is not hydrogen, okay? Now, what you typically have is a whole blend of C1s through C6s that could be coming through there. But this is a binary gas analyzer, not specific to hydrogen. So how can we possibly measure 60 to 90% hydrogen when the background gas or the other gas could be a mixture of C1s through C6s. Well, if you take a look at the graph over here, you'll see if you had very little hydrogen, you'd have a complete mess of a mix here, and you really wouldn't be able to make that hydrogen measurement. But as you get higher in hydrogen content, here at 60% or up here at 90%, you see that that span between the heavy hydrocarbons and the light hydrocarbons gets smaller and smaller to the point where it actually behaves, that background gas behaves as a single gas. And even if you were to get swings from, let's say, pure methane over to a whole bunch of heavies, you're not going to impact the measurement accuracy all that much. So in essence, this becomes what we call a pseudo-binary gas measurement, where the hydrogen is one gas and everything else acts like a single component. And in a case like this, you can use a binary gas analyzer to let you know where you are in that 60 to 90% hydrogen range. This you typically calibrate for 0 to 100% hydrogen, and then you'd get this kind of performance over here, and easy to make those measurements. Now, I mentioned that people are usually looking at moisture content, and Panametrics does make moisture analyzers, both aluminum oxide and tunable diode laser. And here's an example of a system that has the tunable diode laser analyzer for moisture right here on the upper right-hand side. And on the left-hand side, you have your hydrogen measurement. Now, with the XMTCpro, you would not need that other display package up here, and that would eliminate a lot of the wiring that you see here. All you would need is the XMTCpro wired up with a display package, and what you would probably do is move this up a bit to be where this display package is. So that way you could put a window kit and see both displays at one time. And you could probably eliminate a lot of space there also because of that. We would redesign the system to accommodate the lack of need for one more display package. Again, being able to combine measurements into a single cabinet offers you a lot of cost savings. Otherwise, you'd have to have a sample system for your binary gas analyzer and a separate sample system for your moisture content. By combining the measurements into one box, it makes it infinitely easier and saves you a lot of space. We've been talking about hydrogen a lot, and the big thing in hydrogen is now electrolyzers. But 95% of the world's hydrogen is still made by steam methane reforming. And you can see here the equations. Basically, to start off with methane, and you add water, and you get CO2 and hydrogen. And that's how steam methane reforming works. And there's a long form of the equation there on that second to last bullet. And what you're measuring there is hydrogen purity again. You want to make sure you're getting as much hydrogen as you can out of that process. You also measure oxygen here, and you're measuring moisture content. And again, there is cost savings in doing all three of them and getting them into one sample system. Fairly straightforward application. Fertilizer process. As you can see here, I'm not going to go through the entire schematic in the interest of time, but you do have your syngas forming, and then the real application here where you're looking at a binary gas analyzer is mixing the nitrogen from air and the hydrogen from natural gas at high temperatures, and then really at the end of it is the excess nitrogen and hydrogen, which is being recirculated here at the bottom. It's basically understanding what that mix is as it goes back in here again. So there are several measurements to be made here. And then the ammonia plant applications are very similar here too. You have a carbon monoxide shift inlet where you're measuring 0 to 10% hydrogen and carbon dioxide. You're measuring 60 to 80% hydrogen and methane in your methanator exit. CO2 and hydrogen are converted to methane, as you can see here. The inlet to the ammonia converter, 50 to 70% hydrogen and nitrogen. And then hydrogen gas recovery is going to be 50 to 60% hydrogen and nitrogen. Okay. Metal heat treating applications are abundant, and they come in a lot of different varieties, a lot of shapes and sizes. And where do you really see that? You see that in brazing, galvanizing, aluminized steel, sintering, and those applications are pervasive. They can be small little ovens on the manufacturing floor to in huge galvanizing lines that are hundreds of feet long and operating at very high temperatures. So we'll just go through a couple of these applications. Here you could see what would look like a galvanizing line. And what you see is stainless steel rolls going in through these high temperature furnaces with multiple heat zones and then coming out the other side. And in this heat treating process, you do need to control the hydrogen-nitrogen blend, the oxygen level, and the moisture level. And having someone that can provide you all of these measurements in one cabinet, as you can see here, is really ideal. Imagine having to have a moisture transmitter with its sample system, an oxygen transmitter with its system, and then a hydrogen monitor in its own sample system. Well, you can do all of these at once. And the advantage that we have is we have multiple technologies that we can use to measure the oxygen and the moisture. And then you add the binary gas analyzer to make a complete package. Okay. Typically in these applications, dissociated ammonia is being used to give you a 75% hydrogen, 25% nitrogen blend. But some folks need to have either higher or lower amounts of hydrogen, in which case you're either adding hydrogen or adding nitrogen, and needing to make sure that you have that right blend is where that binary gas analyzer comes into play. Doesn't have to be a line like you saw with the stainless steel. It could be a large part going into what's called a bell furnace, and you see a bell furnace over here. And this bell furnace basically allows for large parts to be put into the floor. The cap that you see here is lowered down on there. And then you're looking at nitrogen to purge out the air and the oxygen prior to adding the hydrogen-nitrogen blend. So there are a couple of measurements that can be made here, both an oxygen measurement and a nitrogen-hydrogen blend measurement. These are very straightforward. You don't end up with too much contamination in here. So a very simple filter element can be used. And so you have a sample inlet, a zero gas, and a span gas, and just choosing what you need. And in some cases, because this is typically low pressure, you'd use a pump to pull that sample through. If we jumped into the sexy part of hydrogen economy, all the new stuff, everyone's talking about electrolyzers. And there's a huge move to get very small units or racks and racks of very large units to produce hydrogen. And those can be at point of use, or it can be used for almost anywhere that you need hydrogen on demand, whether it's peak shaving or complete use of hydrogen. And there are really two types of measurements being made here. One is safety, keeping the oxygen level in hydrogen low and the hydrogen level in oxygen low. And the way that electrolyzer works is it separates water into oxygen and hydrogen, and it's basically keeping them on one side or the other of a membrane. If you end up with hydrogen migrating into your oxygen, that's an explosive mixture. And if you end up with oxygen migrating into the hydrogen side, you get an explosive mixture, and you don't need that. No one wants to hear boom in the middle of the night. So that's your safety measurement. But you also are required in many cases to see if you have a quality issue. Maybe you're not getting enough oxygen to cause an explosion, but you may have more oxygen than you really want from an efficiency point of view. So the electrolyzer manufacturer is also checking for quality of their separation. So you have a safety measurement and a quality measurement. And this is where a silver-rated product for the percent of oxygen and hydrogen is being used. And then you have a hydrogen and oxygen measurement, is being used for the percent level, and typically a ppm measurement for the oxygen and the hydrogen. Steam methane reforming is now also finding its way into skid type, smaller scale type applications. And those are being used at fueling stations so that you can actually do hydrogen fueling with hydrogen on demand. So instead of using an electrolyzer, for instance, which is being used in many cases, you might actually have a modular steam methane reformer right there at your fueling stations. And again, what you're looking for is hydrogen purity there. This is a fun application, and we're seeing more and more of this. You're seeing that many folks are taking and moving hydrogen from point A to point B by using the natural gas pipelines. Now, typically what you're finding is that they're blending in as much as 20% hydrogen into the methane. Now, they may be doing it to move the hydrogen from one side to the other and separating it at the other end, or just saying, hey, hydrogen burns cleaner, so I can reduce my carbon footprint and my CO2 emissions by feeding hydrogen into my methane. And then for when it burns, it doesn't form CO2, it forms water vapor, at least the hydrogen does. So you effectively knock down your emissions. The reason you cannot put more than 20% hydrogen into the pipeline is because what you'll end up with is hydrogen embrittlement. That's when the hydrogen starts to impact the pipe material, causing micro cracks and fissures, and then the hydrogen will leak out, whether it be through the walls of the pipe or through all of the different wetted materials where you might have things like pressure transducers, temperature transducers, and other types of fittings. So either you're going to be in the 0 to 20% hydrogen range, or as we're seeing in many places in Europe, is saying no natural gas. We're going to put just hydrogen into that natural gas pipeline and move the hydrogen from point A to point B using natural gas pipelines that are either being repurposed or having needed to be repurposed for whatever reason. Now, you don't get the hydrogen embrittlement if you're just using pure hydrogen. In any case, you still need to understand what that blend is because you don't want to be pushing it above 20%, and that's where a binary gas analyzer is being used. You still have to measure moisture and oxygen to meet the pipeline tariffs, but in most cases, the hydrogen will not be impacting that measurement. We talked about ammonia production. That's part of our energy transition. You're seeing more and more ammonia plants going in, especially where you can power them with a lot of sun, i.e. the North African deserts. Now you have solar panels powering a lot of this. And the reason that they're working with ammonia is because it's very well understood as to how to transport it, whether it be by tanker or by pipeline, or however you're going to transport it, cylinder. It's really part of that energy transition play. So how do we know that the XMTCpro or any binary gas analyzer would work well? That's because we have to understand your application first. And what we ask for is that you fill in an application data sheet, gives us all the parameters. Is this an explosion-proof area? What your gases that you're looking to measure, one and the other? Can it be done using a binary gas analyzer? What your zero gas is going to look like? All depend on this. But as I tell folks, the biggest spot on the form is the bottom section here, which is white space, that we ask you to describe what problem we're trying to solve for you. Okay. What problems have you seen in the past? How can they bind, and that way we can understand how a binary gas analyzer, and specifically the XMTCpro, can give you some value and some benefit. So with that, I open the floor up to any questions that you might have.
All right, just give me a second here. There's a few that have come in. First one, can the XMTC, can this device be used to measure oxygen?
In fact, it can. If you think about where oxygen is just to the right of air. So I said air and nitrogen are at roughly 1. In fact, oxygen is just to the right of that, maybe at 1.1 or 1.2. So you can use this as an oxygen analyzer in hydrogen, okay, as long as you're in the percent level, or for that matter, in other gases, as long as there's enough of a thermal conductivity difference between the oxygen and the other gas. So oxygen and helium, even in limited ranges around in methane, though that would not be the ideal one, an oxygen analyzer would be probably a better way of making that measurement. But if you're looking at differences in, let's say, oxygen and hydrogen or oxygen and helium, yes, very much so you can use a binary gas analyzer to measure oxygen. Thank you for that question.
Next question was with regard to SIL applications. How did you do SIL applications prior to the SIL approval?
So before SIL approval, what we were doing is either one of two methods, providing mean time between failure for the transmitter, and many customers would just accept that data and then keep track of it on their own. What we found was in many cases, and in most cases today, customers are not willing to do all that record keeping. And if they are in a safety application, pretty much everything in that application needs to be SIL rated. The other way to do it is via redundancy, by having two transmitters on separate power supplies with independent 4-20s going back to a control room. As long as those two devices are tracking correctly and consistently with one another, that is a way of giving assurance in a safety system that everything is well. Now, as you saw on one of the early slides, with a SIL rated device, two SIL 2 transmitters in parallel, or for that matter in series, as long as they're in separate power supplies, will give you a SIL 3 rating, an even higher rating. So this is how we did it in the past and how we can do it in the future.
But we have the SIL as opposed to the MTBF.
Correct. Before, all we had is the MTBF or that in conjunction with redundancy. And there are folks that today still believe that redundant measurements provide more value than just the SIL rating. So just because we now have SIL 2 does not necessarily mean that customers will move away from the redundant measurement, because there's something to be said for that.
Oh, I missed one. Are we required to use your sample system?
Are you required to use our sample system? I always like to draw an analogy with a sports car. If you go and buy a Ferrari, the Ferrari dealership will have tires on there. Do you need to use the tires that Ferrari supplied with your car? No. No one's saying that you need to use those tires. You can put on whatever tires you'd like to put on that car, but you do so at your own discretion. Now, in many cases, the sample system requirements for a binary gas analyzer are simple. A sample gas in, a span and a zero gas, and a filter. But in other cases, in some of the more challenging applications like electrolyzers, for instance, if you don't have the expertise or the willingness to do all the work necessary to drop out the liquid water so that you get a representative sample to your transmitter, then that's where we come in. That's where you get the value of having a complete measurement system coming from the vendor. So think of it as a sense of assurance that we're never going to come back and question our performance of our transmitter if we're providing our own sample system and ensuring that it's working well. On the flip side, if you have someone else provide it, or if you're providing it yourself to save a little money, the question is, are you going to be cutting corners on the integrity of the sample system? And then will you get the most value out of that transmitter? So that's up to you to decide. If it's a fairly simple design, you may choose to build it yourself. But if you don't have the confidence that you're going to get that performance correct, then we're there to help you with that. It's far easier for us to do these. We have 60 years of sample system design expertise, along from our moisture analyzers, and 30 years of 30 to 40 years of hydrogen measurement and other binary gas and oxygen measurements for sample system design. So we kind of know what we're doing. We've had experience with it, and we can help you with that expertise.
So you're doing sample systems back in 1990 when you started, right?
Well, that was my job as an application engineer. That's exactly what I was spending most of my time doing, is designing sample systems. Now, we don't have to design them from scratch. I mean, we have a library that we've been building since the, let's say, late 70s going to the early 80s. With, at the time, everything was custom until we saw that we were getting repeat applications. And then why would you start from a clean piece of paper every single time? We would start from a standard design. So for our electrolyzer applications, we do have a standard design that we build from, but then we look at a customer's application and say, how would this standard design work? And if it will, there's no need to reinvent it, no need to do new drawings. It becomes easy to supply, and we go ahead and go down that road. Now, if there are nuances, then we have to account for those. So if we need to add a pump, for instance, if we need a bigger filter because we expect it to be dirtier or dustier, if we have to be more aggressive with liquid removal, those are all things that we have expertise in, but we always start from something that we've done before, so we can at least rely on that expertise and that performance that we've seen in the past.
Smart. Appreciate that.
Oh, that's what we do.
I think I'm caught up. Let's give it one more second for any last second questions popping up. So if anybody has any follow-up questions, just type them into the chat. Nars, looks like we got it covered.
Excellent.
So thanks again for your time and expertise. And attendees, thanks for joining and the questions. We really appreciate that. If you do have questions or specific application questions, please feel free to give us a call at 800-9-LESMAN, 800-953-7626. If you don't know your account manager, just ask for me and I'll make sure you get taken care of. You can also reach me at my email address, johng@lesman.com. Just a follow-up request, if you want to know more about the technologies we support, all these webinars are posted both on our website and on our Lesman Instrument Company YouTube channel. If you've got ideas for future topics, please send an email and let me know the subject that you'd like us to cover. As you see, we've got access to lots of expertise with products and processes. And just let us know and we'll get something put together that makes sense. At this point, if there's no further questions, we'll conclude the presentation. Narj, anything that you wanted to comment on?
Just thank you all for joining us today. John, thank you for giving me the platform to go through this product and this application set. And I look forward to chatting with anyone in the future that has any questions about this. Thank you.
Awesome. Thanks, everybody. Thanks, Narj.